Here is a sentence that should be simple. The animal didn't cross the street because it was too tired. Now, what does the word it refer to? You know instantly that it means the animal, but change one single word. The animal didn't cross the street because it was too wide. Suddenly, it means the street. Nothing about the word it changed. What changed was a word at the very end of the sentence, and somehow that rewrote the meaning of a pronoun 8 words earlier. Getting a machine to do that reliably is the problem attention solves, and it is the single idea that made modern AI possible. Before attention, the dominant approach read a sentence one word at a time, carrying a running summary forward, a bit like taking notes while somebody talks. That works for a short sentence, but by the time you reach word 50, the note you made about word 3 has been overwritten many times over. Worse, it is strictly sequential. You cannot look at word 50 until you have processed the 49 before it, so training cannot be parallelized at all. To understand the fix, you need one piece of background. A model does not store words. It stores each token as a long list of numbers called an embedding. Those numbers place the word at a specific point in a space of meaning, where words that get used in similar ways end up near each other. So king and queen sit close together, and banana sits somewhere else entirely. Meaning becomes geometry, and geometry is something a computer can do arithmetic on. But there is a catch that trips people up. Attention, on its own, has absolutely no idea what order the words came in. It sees a bag of vectors. The dog bit the man, and the man bit the dog would look completely identical to it, which is obviously useless. So before any of this begins, a positional encoding is added to every embedding, nudging each vector in a way that encodes where in the sequence it sat. With that in place, attention starts from one simple question, asked for every single word. Which other words here should change how I understand this one? For the word it, the answer should be animal, strongly, and street, weakly. The mechanism has to discover that from the numbers alone, with no grammar rules. It does that by projecting each word's vector 3 separate ways, into what are called the query, the key, and the value. Think of a library. The query is what you are looking for. The key is the label on each shelf, and the value is the actual content of the book. So every word produces a query describing what context it needs, a key advertising what information it offers, and a value carrying what it would contribute. These are not hand-designed. They are 3-weight matrices learned during training, and learning them well is most of what training a transformer actually is. Now the comparison. For the word it, we take its query and compare it against the key of every other word in the sentence. That comparison is a dot product, which just means multiplying the two lists of numbers together element by element and adding up the result. When two vectors point in a similar direction, that number comes out large. When they point in different directions, it comes out small. So the query for it lines up strongly with the key for animal and produces a high score. Against the key for the, it produces almost nothing. There is one small but important step before we go on. Those dot products get divided by the square root of the vector's dimension. Without that, in a model with hundreds of dimensions, the scores grow so large that the next step saturates and the gradients almost vanish during training. Because the next step needs proportions. One raw score might be 12, another might be -3, and those cannot be used as weights directly. A function called Softmax handles it. It exponentiates every score and divides by the total, which forces them all to be positive and to sum to exactly 1. Now you have a real distribution. 71% of the attention on animal, 18% on street, and small slivers spread across everything else. Finally, those weights get applied to the value vectors. Each word's value is multiplied by its weight, and then all of them are added together. The result is a brand new vector for the word it, one that now literally contains most of the meaning of animal mixed into it. And that is the whole mechanism. The pronoun has been resolved, not by a grammar rule anybody wrote, but by arithmetic over learned vectors. One problem remains though. A single set of query, key, and value matrices can really only learn one kind of relationship at a time. But language has many relationships running at once. Which noun does this pronoun point to? Which adjective modifies this noun? Which verb governs this subject? So a transformer runs several attention mechanisms side by side, each with its own learned matrices. Those are the heads in multi-head attention. One head might specialize in tracking pronouns, while another follows subject and verb agreement. Their outputs are concatenated and combined back together. Researchers have pulled these heads apart and looked inside. Some genuinely do track syntax, with one head reliably linking verbs to their objects across a whole corpus. Others are far harder to interpret, and a surprising number turn out to be redundant. You can prune a good fraction of the heads in a trained model and barely lose accuracy. Then the whole block simply repeats. The enriched vectors feed into another attention layer, and another, often dozens of them stacked deep. Early layers tend to capture local grammar. Deeper layers capture longer-range meaning, and by the top the representation encodes something much closer to intent. There is one more variation you are using every time you talk to a chatbot. When a model generates text, it must not be allowed to see the future. If it could look at the word it is about to predict, training would be trivial and useless because the answer is sitting right there in the input. So the scores for every future position are forced to negative infinity before Softmax, which drives their weights to zero. That is called causal masking. And when a model needs to attend to something other than its own input, the very same machinery covers it. The queries come from one sequence, the keys and values from another. That variant is cross-attention, and it is how a translation model reads the source sentence, and how an image generator conditions itself on your text prompt. Here is why all of this replaced everything before it. Every word attends to every other word at the same time, inside one big matrix multiplication. There is no sequential bottleneck left, which means an entire sentence can be processed in parallel across thousands of GPU cores at once. That is the real reason Transformers won. Not only that attention is more accurate, but that it maps almost perfectly onto hardware built for parallel arithmetic. It does come with a bill. Every word compares against every other word, so doubling the input roughly quadruples the computation required. That quadratic cost is exactly why context windows have limits, and why a large slice of current research is aimed at making attention cheaper. Sparse attention, sliding windows, and linear attention all try to dodge that quadratic term, and every one of them trades away some of the ability to relate any word to any other. But the core idea has not changed since 2017. Every word asks what it should pay attention to, scores every candidate, and rebuilds itself from the answer. That is attention, end to end. Subscribe to ZapByteAI for more AI explainers, one concept at a time.